the actual physical environment of the listener, for which the listener actually has immediate reference. That is, the listener is there in that space. Rendering high-quality room acoustics in XR is essential for a number of reasons. First, obviously for achieving adequate auditory immersion, spaciousness, and envelopment experience. Even more importantly, for achieving the sense of realism and presence. And what seems not to be sufficiently appreciated, it is very important for effective externalization, and it is also crucial for providing convincing illusion of source distance and its width. For example, this AltSpace VR software is fantastic, but it seems to be doing only some very basic room acoustics modeling. So as a result, most of you probably hear us inside of your heads and at the same distance, regardless of how we are in this virtual space from you. Hence, the emphasis of this tutorial will be on fundamental principles and state-of-the-art in room acoustic synthesis, but we will cover also to some degree its integration with binaural rendering. High-quality room acoustic simulation is a conceptually solved problem. However, the main challenge in XR is that it needs to be done interactively in real time, using often extremely limited resources. In order to address this challenge, it is critical that we synthesize and render only soundful aspects which are perceptually relevant. And therefore, in this tutorial, we will present first fundamentals of room acoustics, followed by relevant psychoacoustics that governs room acoustics perception, and then how the two are combined to achieve computationally efficient room acoustics modeling. Then we will touch upon the integration of room acoustic synthesis with binaural rendering, provide a brief overview of some open source SDKs for XR audio, and then conclude. As XR is a broad topic, in this brief tutorial we can provide only a high-level coverage, and we will have to refer you to further reading, for which we provide an extensive list of references at the end of this of our slides presentation. So I'm handing over to Enzo now.
Thanks, Zoran. And thanks everybody for joining us. This is quite something, I have to say. I'm not sure if this is the future, but yeah, let's see. Let's see how this goes. And okay, so I'm going to start by just giving some fundamentals about room acoustics. Then we're going to move on to elements of perception of room acoustics, and then we're going to move on to the perhaps the core of this talk, which is on room acoustic models. Okay, so how does sound propagate? We have an excellent model for sound propagation, both in free field or within enclosed spaces, and that's the so-called wave equation. The wave equation is this equation at the top. Unfortunately, I don't have a pointer, but I'll try my best to walk you through the slide. And the wave equation is a partial differential equation, which is the triangle sign is a Laplacian, and this represents second-order spatial derivatives, and P represents the instantaneous pressure, C is the speed of sound, and S is the source distribution. Zoran, I believe you're not muted. Would you mind? Thanks, Zoran. So in order to solve this type of differential equation, one needs both initial conditions, which represent the state of the pressure field at a given point in time, and the boundary conditions, which represent what's the behavior of the pressure field at the boundary. And the main issue here for us is that this equation, although it's quite elegant and compact, it only admits closed form solutions in very few cases. And some examples of cases are in free field, or when the boundary is a cuboid, for instance, or at the external, at the exterior of a sphere, and so on. And that's the main problem for us, which we're going to deal with later during the room acoustic modeling part. So what can we say about this equation? Some very useful information comes from considering the wave equation in frequency, and that means having a sound source which is essentially an oscillatory sound source, a complex exponential. When we do that through variable separation, we obtain this other form of the pressure field here, where we have a summation of psi terms at the numerator divided by omega squared minus omega squared m minus 2j psi m omega m. Here omega is the angular frequency, x and x first are the observation and the source position respectively. Omega m are the respective modal frequencies, and psi m are the imaginary parts of the eigenvalues of the problem, and psi m are the so-called eigenfunctions of the problem. So here, each of these elements in the summation is a so-called mode, or in some cases resonance mode. Why is that the case? Well, you can see that here at the denominator, if you see psi m it were to be equal to 0, for instance, then you would see that for omega equals omega m, then this mode, this element of the summation would go to infinity. In most cases, psi m are not equal to 0, and therefore you get a more smooth behavior, which is the behavior you see in the figure in the bottom left figure. So at the numerator, on the other hand, you have these eigenfunctions, and they dictate how this sound field changes as a function of space within the enclosure. For instance, in this case, in the bottom right corner, we have an example of an eigenfunction for a rectangular room, and we can see that there are some certain positions which are called nodes and antinodes, or maxima and minima of our function. So why is this important, and how do the omega m behave? So the values of the resonant frequencies, these omega m values, strongly depend on the boundary condition and the type of enclosure. And what we do know is that their density increases as frequency squared, meaning that at lower frequency we have fewer omega m's, and higher frequencies we have a larger distribution of frequencies. Okay, so my apologies. So I can see some not smiley face at the background. Okay, yeah, thanks for that's also quite something. I'm not sure why it was untoggled, but I hope it's okay now. So so this is an example, for instance, of a room where we can see a certain number of resonant frequencies. At the lower frequencies range, we can see that the resonant modes are better separated. They're more there is a sparser distribution of frequencies here. And beyond a certain point, and the number of modes is so high that actually they start overlapping each other and start behaving in a more random or chaotic fashion. Now, the transition frequency between these two areas where the modes are sparse or overlapping was one of the contributions, seminal contribution by Schroeder. It's called the Schroeder frequency. This is the value of which is calculated as 2000 square root of T60 over V, where T60 is the so-called reverberation time. We're going to define it in a couple of slides, over the volume. And just to give an example, a couple of examples here, for instance, for a bathroom, which is quite small, the Schroeder frequency is 307, just an example, around 400 hertz, whereas for a larger space, a concert hall, it's only 54 hertz. And what this tells you is that for larger spaces like a concert hall, really the Schroeder frequency is so low that pretty much all you see is a large number of modes overlapping and turning into a more chaotic frequency response. Whereas for a bathroom, this is 400, so it's the area below the Schroeder frequency can be really perceived. And one of the main features of this is that when the modes are well separated, sometimes you perceive that as a kind of metallic sounding reverberation. So what happens in the time domain? Let's think about, for instance, having an impulsive sound source and in the time domain. And if we look into a certain position in space, you can imagine having a microphone and somebody shooting a pistol or and we observe in time how this behaves, we see what we obtain is a so-called acoustic impulse response, and which is this figure on the right. What we observe here is a certain direct sound, some sparse early reflections, and this correspond to reflections that bounce perhaps 1 or 2 times off the walls, and in this region they are quite sparse and can be discriminated, at least on the time axis on a plot. Whereas later the number of reflections increases so drastically that they become very dense, and also in this case they start to behave chaotically, meaning that even small changes in temperature in a room will change the exact structure of this region here. We call this late reverb. Spatially, this in the late reverb part, typically you have reflections coming from all around, and whereas in the early part, these are well localized in space and from certain specific positions. Now let's make some definitions here. The equivalent in the time domain of the Schroeder frequency is called the mixing time, and that is the transition point between early reflections and late reverberation. What I mentioned before, the reverberation time, is the time taken for cumulative sound energy to decay 60 dBs below its initial level. This is a very important parameter. You can think of it as a certain time when where you stop hearing the reverberation. And one can also consider the actual sound energy instead of the cumulative sound energy, but this definition is more resilient to statistical noise or statistical fluctuations. The direct to reverberant energy ratio, which is quite important for the perception of distance, is the ratio of energies of early reflections and late reverberation. We're going to come back to this in a few slides. And the critical distance is the distance at which energies of the direct sound and the reverberation are equal. And this is a strong feature that affects speech intelligibility. So just to start, I'm just going to play some examples of some acoustic impulse responses. Probably some in the audience or many in the audience are already familiar with this, but I thought it would be useful nonetheless. So let's have a listen. So this is an example of a church with a reverberation time of about 2 seconds. Played back 3 times. This is an example of a room, a much shorter version. And this is a Guinness World Record. We're probably not going to play the entire thing. Oh, it wasn't amplified again for some reason. I better check a few times. I'm not sure if I'm...
Zoran, this is Lawrence. Can you hear me?
Hi, Lawrence. Yes, I can.
Yeah, I just thought this is a momentous moment for me. This is the first video sample that we're playing in this space, and we've had some issues. So can we for me, I was able to hear those 3, all the audio and the video all played seamlessly. Could we see from the room? Was anybody else able to see and hear the video? Can we get some? There's a few. How about and how about who was unable to either see the video or hear the sound? Put a sad face emoji up. Oh, it looks like everybody got it.
Great,
okay, well,
fantastic.
I've interrupted your workshop for no good reason, so I will shut up now and let you get on with it.
No worries. Okay, thanks, Lawrence. Okay, so this was, as I said, this is still playing back. So Lawrence, you didn't interrupt anything, I guess. And this is indeed a Guinness World Record for the longest reverberation time. It's 75 seconds. Actually, at low frequencies, is even longer. Okay, so let's have a look at the main and very high-level overview of the main phenomena that govern the acoustic impulse response and that are embedded into the wave equation. One has to do with just propagation in space, propagation of sound waves in space. And the 2 phenomena here are distance attenuation. This is due to the fact that over spheres, the energy needs to stay constant, and that means that in a specific point in space, the energy has to decrease. This is called spherical spreading, and the law that governs that is the so-called inverse square law. This is just a geometric feature. And the effect of this is that for every doubling of distance from 1 to 2 meters, 2 to 4, and so on, there is a 6 dB drop in level. The second phenomenon is hair absorption, and this is mostly caused by heat losses due to friction. And you can see in the top right corner that as the distance increases, the air absorption is actually quite frequency dependent, meaning that at higher frequencies that there is a larger attenuation. This is particularly relevant for very large spaces like churches, for instance, and dictates also the fact that reverberation time at higher frequencies is typically lower. The second slide, at least on this, has to do with reflections. Whenever you have a sound wave hitting a certain boundary, this will generate a specular reflection, and depending on the material, a more or less energetic diffuse sound field, diffuse reflection. Also, whenever you have some sound waves hitting boundary, you typically have some form of energy loss, which is typically also dependent on frequency. And it really depends on the different materials. So for instance, glass is gonna have a lower energy loss at the boundary, whereas a carpet, for instance, might be quite lossy. Typically, it depends on the room size. Whenever a room is smaller, you have so many reflections that that the losses at the boundary is much larger than the losses in air. And here I'm going to actually hand over to Hseyin.
Yep. Now I'm going to continue with source directivity, which also has an important role by its profound effect on room acoustics. The importance of source directivity is easy to imagine when you consider listening to a speaker when you're in front of them or behind them. There is typically a 20 dB decrease in the level that you can record with a microphone, and you can hear it as well. So depending on where you are, the direct path level in a room will substantially change due to source directivity, so as the early reflections, but the reverberation will more or less stay the same, statistically the same anyhow. In the figure, you can see the actual directivity pattern for a violin, and depending on where you measure the room impulse response, your direct path and the early reflection pattern, as well as the whole perception of room acoustics is going to change. And one thing to remember, again, about the importance of source directivity is that its effect is so profound that critical distance also changes with directivity gain, and with it, how intelligible a person is within a room with respect to distance. And from an XR system design perspective, different sound sources have to be simulated for their directivity patterns to increase realism. However, well, it is not easy to measure source directivity. It's not trivial. Now, you have to carry out measurements in an anechoic chamber, and with inanimate objects like loudspeakers, it's quite easy to do that. However, if you have human speakers, then it becomes a big mess, because you need to make sure that your speakers have to stay stationary, and then you have to measure in many directions around them. The figure is from an excellent paper by Katz, Prezat, and Alessandro from 2006. You can see that human voice becomes substantially more directional for increasing frequency. That is something that should be included within any room simulation which goes into an XR system. And on the left panel, you can see how this measurement is carried out in an anechoic chamber. You have to have a circle of microphones around the speaker, and mind you, you cannot get your human speaker to generate synthetic sounds like tones or pseudo noise. So you're practically bound by vowels or other sounds, other speech-like sounds. From a practical point of view, formats such as the common loudspeaker format or spatially oriented format for acoustics can be used to store and deliver source directivity data. When an obstacle blocks the line of sight between a listener and a sound source, occlusion occurs. If you have partially transparent barriers, you're going to have transmission through that barrier as well, and the sound that impinge on such barriers will be low pass filtered by that barrier. So that's the transmission through the obstacle. You will obviously have sound waves traveling around the obstacle, resulting in what is called diffraction. Now, diffraction is something which is not easy to handle. It is very complex as a phenomenon, and it depends on the position of the sound source and of the observation point. So the figure in this slide, the left figure, shows 3 distinct regions where diffraction occurs differently. In the first region, the impulse response comprises the direct path, an early reflection, and the diffraction component, which has a negative phase. In the second region, only the direct path and diffraction component, which has a positive phase, are present. So you don't have the reflection, you don't observe the reflection in that second region. And in the third region, only the diffraction term is present. And one thing which is quite hard to pin down with edge diffraction is that its directivity is not easy to handle. So when do you have negative phase, when do you have positive phase, what is the level of the diffraction term? So this is not easy. Luckily, there are some analytical models of edge diffraction. However, the number of parameters and the computational costs involved are typically very high for interactive applications. One of the analytical models, which is one of the most famous actually, Biot-Tolstoy-Medvin model, uses all the parameters that you see on the figure on the right, like the receiver and source position, the wedge angle, etc. And it still works only for infinite wedges. So when you have a finite wedge, you need to use mostly use numerical methods like secondary source models. So all acoustical phenomena in a room are certainly important from a physical point of view. However, it is mainly unnecessary to consider anything which does not have perceptual importance in a more user-oriented context such as XR. So if you can't hear it, why bother with it? So then we need to ask the question, how do we perceive sound in rooms? Now, perception of room acoustics has been a topic of interest for the good part of the past century, as well as this century. So there's been quite a lot of research being done on this topic. We're just going to cover some very important aspects. So we're not going to cover all different things related to perception of room acoustics, but let's start. So the way we perceive sound in an enclosure is substantially different than in acoustic free field. Early reflections in rooms affect our perception of how spacious and enveloping the environment is, and also changes the perceived size of a sound source. While we're not sensitive to the precise structure of late reverberation, reverberation time is going to affect the impression of size of the room. Reflection build-up density affects the perceived texture of reverberation, and mode density, when it is insufficient, can yield metallic sounds. Now, here are some of the important psychoacoustical phenomena which are related to the perception of sound in rooms. Most fundamental of these is the precedence effect, where the auditory system assigns a higher weight to the first arriving sound source. In the classical precedence effect experiment, a broadband click is presented from the left loudspeaker or the right loudspeaker, depending on how you're carrying out the experiment, and a delayed copy is presented from the other loudspeaker. The applied delay determines the perceived direction of the sound source. So when the delay is 0, you perceive a single auditory event. You can follow this from the figure on the right, when the x-axis is the delay and y-axis is the direction of the auditory event in that figure. So when the delay is 0, a single fused auditory event is perceived at the midline of 2 loudspeakers. When the delay is increased up to a localization dominance threshold, indicated as tau low in the figure, the auditory event shifts towards the leading loudspeaker, and increasing the level further does not change the position of the auditory event. So we have a fused and single auditory event, which is slightly more diffuse than playing it back through a single loudspeaker. Then when the delay reaches a temporal echo threshold, you start to hear a direct sound and a reflection from the 2 loudspeakers. So you hear 2 auditory events. You don't hear a fused auditory event anymore. So that is one of the most important phenomena which allow us to hear sound sources, hear the directions of sound sources in rooms, because in rooms there are many reflections. Baron investigated the effect of early reflections from a concert hall acoustics perspective and found out that lateral reflections are very important in the perception of room acoustics. The figure in the slide gives a good idea about how even a single reflection incident from 40 degrees azimuth with respect to the direct sound strongly affects the perception of the sound field. In this figure, the x-axis shows the delay of the early reflection with respect to the direct sound, and the y-axis is the reflection level, again, with respect to the direct sound. Then you can see that for a range of delays and levels, the reflection will be inaudible. So any reflection within this region will not even be registered by the auditory system. It will have no effect whatsoever. However, above this threshold, the early reflection changes the perceived spatial impression of the sound field. For a range of delays and levels, the early reflection is perceived as a disturbance in the form of an echo. So that is when you have a large delay and a large level with respect to the direct sound. So in general, higher the delay and lower its level, should be, so in general, higher the delay and lower its level should be to not cause any disturbance. Similarly, if the delay is very short or its level is very high, the perceived direction of the auditory image will be shifted. So you're going to hear an auditory image which doesn't coincide very well with the visuals on the screen, for instance, or visuals in your field of view. Further, for a wide range of delays and levels, the reflection results in tonal coloration due to the comb filtering effect that it causes. And again, this is for a single reflection. So this is not for all the reflections in your room. So when you consider different directions, reflections from the ceiling and the floor, you're going to have a combined effect, which is going to change how the direct path or the sound which we're listening to for its direct path is going to be changing within the room. So reverberation, when taken as a whole, has complex effects on many different perceptual attributes, such as spaciousness, apparent source width, distance, depth, apparent room size, presence, and envelopment. And among all these attributes, most notably, presence, distance, and envelopment are hugely important for a successful experience, which means for delivering a successful XR experience, room acoustics has to be dealt with in an appropriate way. So in summary, for this little portion talking about different aspects of how we perceive sounds in rooms, we talked about the constituent parts of a room impulse response. We briefly mentioned how waves propagate in air and the boundary conditions that determine its behavior in rooms. We discussed the modal description of reverberation and the importance of frequency modes, especially at low frequencies. And we talked very briefly about the most important perceptual phenomena that affect how we perceive sounds in rooms, as well as why an accurate rendering of early reflections is essential, while precise structure of late reverb is less important. So I'm going to hand this over to back to Enzo for.
Okay, thanks, Hseyin.
Yep.
Yeah, thanks, Hseyin. Okay, so let's move on now to how, starting with an overview of the different room acoustic models that are available. And we don't have nearly enough time to give a clear idea about every model that has been developed over the past 50 more years. But I can refer you to some papers, two papers by Vesa Valimaki and others in 12 and 13. We're actually going to share the slides at the end of this. I'm going to ask Lawrence how we're going to be able to do that, where you can actually access all those references. And 12 is a paper called 50 Years of Artificial Reverberation. Lauri Savioy is a co-author, is actually in this room. You can talk to him at the end of the talk as well. And the second paper is aptly named More Than 50 Years of Artificial Reverberation, which was presented at another AES conference a few years ago. So I just want to give as just an idea of what the different classes of models that are available. One important class is the so-called wave-based models, and here we take the wave equation that we saw earlier, and we actually try to solve it on a computer. And this involves some form of discretization of the wave equation, and that means either presenting the sound field in the time domain or frequency domain and discretizing it in the one of those two domains, and also discretizing space, which means typically either discretizing the boundary, and we'll talk about the boundary element method in that case, of the volume. And one example of the latter is so-called finest difference time domain, where the first step is essentially to replace the time derivative that we saw earlier into finite differences. This converts the wave equation to a set of linear equations that can be more or less easily solved. Now the wave-based models are the highest, the class of models that allows for the highest accuracy available to us. The issue is that this comes at a cost of high computational complexity. And although certain advancements have been done in the past, for instance, on how to run these models on GPUs, still as of today in XR, this is still quite considered quite expensive. However, before moving on, I would like to show you a couple of videos that I find quite fascinating. This is an example of a finite difference time domain simulation of a rectangular space, and this was thanks to Nicola Antonello for providing this video. And you can see that even for such a simple domain, like just a rectangle, the sound field becomes quite complex pretty quickly. A second example, which was thanks to Brian Hamilton at the University of Edinburgh, which makes that point even more clearly, is the following 2D wave simulation of a concert hall, which I find I could watch this for many hours, I believe. And here you can see how sound reflects and diffracts over the seats and the different parts of the concert hall. So once again, the computational complexity of these models is quite high. It typically depends on the size of the volume, but that can also mean hours of simulations, so let alone real-time operation, which is what we want for applications in XR. So a class of models that reduces the complexity, but also reduces at the same time also accuracy, is the class of models that we call geometrical acoustic models. And these models, they approximate sound propagation using rays. So we're going to take a look at those in a couple of slides. The other class of models is called delay networks, and delay networks are typically IIR filter, typically recursive filters that do not aim to model physically a space, but try to render some type of pleasing reverberant sound. Now, these models have extremely low computational complexity. In fact, they were historically the first type of artificial reverberators because in the digital domain, at least, because they require so few operations compared to all the other classes. Of course, the drawback is that, as I said at the beginning, there is no physical accuracy. So you're not modeling any specific physical space. You just want to get some pleasing and, to some extent, believable reverberant sound. Just to mention also, in some cases, it is possible that we have access to a real space with the desired impulse response, with the desired room acoustic response. In that case, we can just measure the impulse response, just like the examples that we saw earlier, and then we can use convolution to obtain the output for any desired input. And that can be somebody speaking or a gunshot in a first-person shooting video game. Now, the issue with this is, of course, we need to have access to physical space with the desired characteristics. This is most of the time not possible, but also convolution is a very computationally complex operation. If we run a straight convolution, just really implementing the definition of convolution in time domain, we can make an example. If we have a sampling frequency of 50 kilohertz and a reverberation time of 2 seconds, we have 3 sound sources and 2 output channels, then this would require 60 billion floating points operations per second. So just to give context, this is roughly equivalent to having 20 dedicated CPU at 3 gigahertz running, very roughly. Now, most of the time, even if you use this measurement-based method, you would probably not use a straight convolution, you would use an FFT convolution. However, FFT convolution adds a certain delay because you have to gather the data and then calculate an FFT. However, there are also some low latency algorithms. Even in that case, though, the convolution remains a computationally complex operation. So let's now take a step back and again, what are the main requirements we have for XR? Well, we want low computational complexity. This is not just because perhaps our video game has been assigned very few computational resources, but think in the case of AR glasses, you also want to save battery power. At the same time, you want to be as accurate as possible. Physically if possible, but if that's not possible, you want at least some high level of perceptual accuracy. And within the classes of available room acoustic models, the ones that are most suitable for these applications are geometrical acoustic models and delay network models. And we're going to take a look at these for the next few slides. So I want to start with the image method, which is a very commonly used geometrical acoustic model. And this is the image method is based on a very simple idea that if you have a source and a wall, infinite wall, at least as an approximation, the sound field in this lower half space is actually equivalent to having no wall and 2 sources, one of which is the mirror image of the first one. You can think of this really as if you were replacing a wall with a mirror, and instead of seeing the wall itself, what you're seeing is a source and its mirror image. This is an actual exact approximation, actually no approximation at all. This is an exact equivalencing for a specific type of boundary condition, which is a rigid wall, which is a lossless wall that is not typically encountered in real world. When the wall is not rigid, then the resulting sound field of this is an approximation. Now, but how can we use this in a more typical case where you not only have one wall? If you have multiple walls, what you do is you repeat this process. You remove the wall and mirror, not in this case, not just the source, but the rest of the world, and you keep on of removing walls and mirroring the world until you only have image sources. Now, in the case of a rectangular room, what happens in this case, and again, think of the mirrors all over the place. What you would see is all this distribution of mirror images, which is an infinite lattice of these mirror images. Some work by TU Delft in the reference number 18 has actually exploited also something you can perhaps notice in this figure, which is the fact that this clusters of 4 images, it's actually periodic. And this can be used to obtain very fast rendering in multiple positions in a room. Now, also in the case of non-rectangular rooms, it is possible, and Boris has proposed this, I believe, in the 80s, end of 80s, where the disadvantage in this case is that one needs to calculate visibility for each of these mirror images. And because the number of mirror images increases so fast, this is actually quite a demanding operation compared to the rectangular case. Now, in another very popular geometrical acoustic model is the so-called ray tracing. Here we have a source that emits a certain number of rays in a certain number of directions around the source. You can see the figure in the bottom left corner, and you can follow each of these rays and either have specular reflections, which is the basic ray tracing, so to speak, or when one of these rays hits a boundary, you can also model diffraction if you want, modeling the edge as effectively as a secondary source, which generates new rays. Also scattering. Whenever a ray hits a boundary, then you also create some other rays in that position. Now, how do you build how do you get an output for this? This model, just like the image source, gives you a acoustic impulse response, a room impulse response. And in this case of ray tracing, you look into the position where you want to observe the sound field, and you create a volume around that point. And then whenever there is a ray passing through that, you can record the time and its amplitude. And now here, I'm not going to talk about this, but you can imagine that the choice of how big or large this volume is quite critical, and also the number of rays. Also, this is quite a flexible model because the rays can be weighted, for instance, using source directivity, as Hseyin has briefly discussed earlier, or you can also filter it, having, for instance, to model frequency-dependent wall absorption whenever one of these rays hits a boundary. On the bottom right corner, you can see a ray tracing simulation for a more complex space like a concert hall. Lastly, for the geometrical acoustic model, I wanted to talk about beam tracing. In beam tracing, you instead of casting rays in the space, you cast beams, as you can see in the figure on the left. And whenever you hit, for instance, in this case, we have a room maze seen from above. Whenever we have a certain aperture, like a door, for instance, these rays can pass through, these beams can pass through that aperture, and then they get reflected in the specific room or across rooms. Now this, at the same time as doing this geometric calculation, one can build a so-called beam tree. And the beam tree states whenever there is a reflection, in which space it is, and you can see an example of a beam tree on the right. Now you can imagine here that if the observer moves, the operation that you need, as opposed to ray tracing, where you have to rerun completely the room impulse response, in this case, you can calculating the room impulse response is just a simple lookup into this beam tree, where you see in that specific position every beam that passes through that position. And that means that moving observers are very simple to simulate in this case. The drawback is that whenever the source moves, one needs to recalculate the beam tree, and this is a very complex operation. However, there have been also advantages in this field by Augusto Sarti and using the ray space transform. I can point you to reference 23. Now, compared to ray tracing and comparing all the geometric acoustic models together, the main advantage of ray tracing is that complexity can be easily controlled through, for instance, the number of rays. It can model edge diffraction and scattering. The disadvantage, however, with respect to the image method, for instance, is that there is no guarantee of catching all the reflections. So you can imagine that if you don't use enough source rays, then it is possible that you miss one first order reflection, that is a reflection that bounces just once off a wall. And this is quite a problem if, for instance, you want to model well early reflections. The image method, on the other hand, guarantees obtaining all the reflections up to a certain order, and that's the main reason why it's preferred to calculate the reflections. However, as the order of reflections increases, or if you remember the lattice that we saw before, if you look into image sources that are further and further away, the computational complexity becomes very high, and to the point of being, in some cases, unmanageable in real time. Also, something else that we need to point out is that all of the above methods, they output an acoustic impulse response, so you still need to run a convolution with all of these. And as we said, this is quite computationally heavy on its own. So you have the calculation of the acoustic impulse response, which can be heavy, and the calculation of convolution, which can also be heavy. Now, if physical accuracy is not in it at all, then perceptual models, they actually provide a better option. And this is a paper that we've presented, I believe, a couple of years ago in the IEEE Signal Processing magazine. It gives an overview about these models, and just a very often, we don't have time, unfortunately, to go into detail of all of them, but a very simple and widely used approach is the following, where we we separate the treatment of early reflection from late reverberation, also because perceptually this does make sense. As we said before, early reflections, as opposed to the late reverb, the exact position of this early reflection matters. And in that case, you do use what in this figure is a top delay line. What this means is that we really model explicitly and precisely the early reflections, whereas for the second part, the late reverberation, we use some perceptual models, which are typically delay network based models. Now for this late reverb part, this is the early part, the early reflection part is of course trivial, but the late reverb, we need to take care to render it with certain features. One is that it has a smooth decay, and that means having a high density of reflections. And also needs to have a smooth frequency response, and that means having modes that are close together, so that, as I said before, you don't perceive the reverberation as sounding metallic. So just to give an idea of the design approach that is used here, one ideal late reverb would be exponentially decaying white noise. And of course, we could use exponentially decaying white noise, but that would mean, however, calculating a convolution for this. So we want something that is a lot faster than that. And something that provides such a speed is a so-called feedback delay network. This is a very a simple recursive filter, as you can see in the figure, which is a generalization of Schroeder's reverberator. And the main idea here is that we have a certain number of branches at the bottom that undergo certain delays, and these are fed back through a so-called feedback matrix. And we need to be careful, however, how we design this scattering matrix and these delays. And one approach is to design this characteristic by starting with a lossless prototype and try to obtain a noise-like reverb, and then add losses to obtain a certain desired reverberation time. Jot and Kanye, they have in 1991, they have made certain contribution here, and they defined some process to design these delays and the feedback matrix. Also, Roquette and Smith in 2002 and made also advancements in FDNs by proving equivalence with digital waveguide network, which we're going to discuss in a second, and also defined circle and feedback matrix to increase efficiency. More recently, Schlecht and Habetz have made a number of extremely useful contributions in this area by defining time-varying feedback matrices by analyzing in mathematical detail the lossless, as a class of lossless matrices called unit lossless matrices. They've also obtained closed form and approximated formulas for echo density and defined a new procedure for the delays to obtain certain desired mixing time. So that, let's move on now to digital waveguide networks, which I mentioned briefly earlier, which were proposed by Smith early in 1985. Here we see a digital waveguide network is really, what it says on the tin is a network of digital waveguides, and a digital waveguide is nothing more than really a delay line, bidirectional delay line. So you can see here in the figure on the left, you have a certain input coming into the scattering node, with this, which is the name that we give to this red bubbles, in the case scattering node number 2, which, as the name suggests, scatters energy across all the other delay lines. These delay lines have a delay, for instance, of 100 milliseconds, 1.5 seconds, or 500 milliseconds. They're just made up numbers for these examples. Once the sound wave reaches the other node, this is again scattered in all the other directions. And for instance, when you have scattering node number 1, in this case, we chose in the topology of this example to take the output from that node. Now, why is this used is because the echo density, due to the almost fully connected structure of these nodes, is quite high, and that gives a believable reverberation tail. Now, another advantage of this approach is that it can be interpreted as a network of acoustic tubes, which I find quite fascinating. Now, the main problem here, however, is how do we exactly set the parameters? How do you set the delay line lengths, the network connections, and the scattering matrix? These are all open questions. And one way to define that is something we proposed called in 2011 called scattering delay network. This was based on earlier work by Smith and Karelainen. And this corresponds really to a digital waveguide network that is based on characteristic of a physical room. So you see here on the left, you see a rune sim from above where you have that network. This is really digital waveguide networks, and the scattering nodes here are the points at the boundary. And here, the scattering nodes are connected fully, meaning that all scattering nodes are connected to all other scattering nodes, whereas a source is connected with monodirectional line to the scattering node, and each scattering node is also connected with monodirectional delay line to a microphone. And this admits two interpretations. One is an approximation of the image method, or geometrical acoustic methods that we saw before, and the second is an interpretation as a physical network of acoustic tubes. Now, just to start from the first interpretation of this, you can see here three examples of first-order reflections. And by first order, we mean sound rays that bounce off a wall just once. And the first example on the left is really a first-order reflection. We have in blue the actual first-order reflection. And when we consider its how this is rendered within the scattering delay network, this is exact, right? We have a delay line that goes from the source to the scattering node and from the scattering node to the microphone that provides the actual exact time delay for a first-order reflection. That means that this network of delay lines provides exact first-order reflections. Now the story for second-order reflection is different because, as you can see, the blue line is an actual second-order reflection, mirrors a specular second-order reflection, and this is not contained. There is no path delay within the network that provides exactly this time delay. And this also depends on which specific second-order reflection you consider. In the left case, the approximation, there is an approximating path within the network that is quite close to the actual second-order reflection, whereas on the right-hand side, the third at the bottom has a more a coarser approximation here. However, the important information here is that early reflections are more important, perceptually speaking, whereas higher order reflections, which undergo coarser approximations of this type, they're not rendered exactly. At the same time, though, this is extremely computationally efficient. So that's the key here. Perceptually important information is rendered accurately. As the order increases and the structure of the reverberation tail is not that important, this is approximated more and more. The second interpretation is to see this network as a physical network of acoustic tubes, and it can actually be proven that this is an exact approximation. Oops. Sorry, I'm not sure what's happening, but thanks everybody for making this emoji. I hope that as soon as that happens, that it wasn't too long that I was without this amplification of my voice. Anyways, as I said, so on the right-hand side, you see this visualization, a rendering of this network of acoustic tubes. And this network of acoustic tubes is SDN is an exact model for this network of acoustic tubes. So you can really imagine having a sound source, which is represented by one of these spheres in the figure, and putting your head where the other sphere is, and listen through this network of acoustic tubes. Now, what's the key here is that the actual room on the left that you see shares a large number of perceptually important features with the network of acoustic tubes on the right. And this includes T60 and echo build-up, and while at the same time being extremely faster to model really here. So because on the right-hand side, you really just have a network of delay lines with very few operations. However, as I said, this network shares important features with the full room. So this, I'm not going to go in detail of these plots, but these different plots show how well this network of acoustic tubes performs compared to the image method, for instance, in terms of rendering correctly reverberation time or rendering correctly the buildup of echo density, and that's the figure at the center, while at the same time being 1 to 2 orders of magnitude faster than convolution alone. So not just the image method or any calculation of impulse response, but even convolution alone. So another advantage here is that all the parameters of the model are derived from physical properties, which means no hands-on tuning. And as we're going to see in a few seconds with Hseyin, this also, because there is a physical interpretation as opposed to other types of delay network models, this allows for specialization. Also, we believe that this is a more elegant solution than having separate early and late modules. So I just wanted to show you some examples here where we're going to have the 3 different models randomized, and we're going to make you listen to a sound reverberated through these 3 models. One is SDN, the other is the image method, and another one is FDTD. So first we're going to start with the anechoic example here. And now randomly I'm going to play one of these 3 models, and I want you to think which one is which. Okay, so again, I want you to think which one is which, and the big reveal is that the first one was FDTD, the second one was the network of acoustic tube, SDN, and the third was the image method. So now let's listen again with that knowledge. The first is FDTD. The second one is the network of acoustic tubes. And third is the image method. And just once again, remember that FDTD is a lot more complex than SDN. Hello, somebody on the stage? Okay, so also okay, my computer crashed for a second. Yep. So again, you have the blue dot here represents the soprano, and I'm not entirely sure what happened.
Sorry, Enzo, we were having
Yeah.
some odd issues, just the surreal nature of AltSpace. Could I trouble you to go back to the beginning of your demonstration video and take it from there?
Yeah, will do.
Now,
I hope that.
Yeah, the problem is that when you return to that slide, it may
Not start.
It may not start from the beginning. So let's
Indeed.
give it a go. Let's see what happens. Sorry about that.
Let's try it out. Okay, good. So here there is a more complex demonstration, and this is the SDN model here. And there is a number of sound sources, but they're only visualized in the soprano that is in front of you. And this is supposed to be played back through stereophonic loudspeakers. This is not yet a binaural demo. So I can see some frowny faces. I'm not entirely sure what's going on. Some happy faces, some love, and some frowny faces. So a bit of mixed messages. Can somebody let us know if there was a problem?
Yeah, I'm not sure. I know that for some of us that worked fine. Out of curiosity, again, you guys are the guinea pigs because you're the first ones here. Can I see just a quick happy emoji for everybody who heard that audio demo and it sounded right? Okay, quite a few.
Okay.
And then could I see sad faces from people who did not hear it correctly? A few more just to get, yeah. All right. So I think probably our best bet at this point, Zoran, is to, or Enzo, is to just continue. And
Yeah,
my
let's.
apologies to anybody. You can always try re-entering the space if you want to give it a shot, and maybe that'll help you individually, but I don't
Yeah.
think we'll reset again.
Yeah,
Thank
because the somewhat random position of the frowny faces and happy faces, I would guess it could also be related to connection speeds of different people, and maybe there is some more compression for some than others.
Who knows?
Just a guess. But who
Anything's
knows?
possible.
Yeah. Okay, so there is a number of people that have been working on SDNs. So Stevens and others, they've extended to Besa Valmaki, they've extended to second-order reflections. And implemented direction-dependent scattering, and also worked on modeling of outdoor scenes. Schlechten they've also worked on the specific shape of the scattering matrix. And also we've been working on perceptual experiments where we've actually shown that in terms of naturalness, SDN behaves very similarly to FDN networks, and actually has a higher naturalness than FDN networks or the image method. And we've also been working on connected spaces for this with some unpublished results. Okay, so just to summarize this model, room acoustic model part, we have a very wide variety of room acoustic models. Wave-based models are the most accurate ones available, but they're computationally expensive. Geometric models, they make a ray-like assumption for sound propagation. They have lower complexity, but also lower accuracy. And perception-based for some reason it did not amplify my voice again. And again, perception-based models, they're very fast and they attempt to reconstruct only perceptually relevant features of reverberation. And so with that, I'll hand over to Hseyin.
Muted, I guess.
Yeah, we can hear you now.
Yeah, excellent. So as far as mobile XR experiences are concerned, binaural rendering seems to be the only feasible method. More specifically, in what follows, we're going to talk about the fundamentals of binaural rendering and how binaural rendering can be integrated for presenting room acoustics in XR applications, in immersive applications. So human body, and especially head, have complex shapes which will diffract and shadow sound. These effects can be modeled via computationally expensive wave-based models, which are not preferred in general in interactive contexts. A more usual approach is measuring responses from binaural microphones or actual people, using the assumption that the acoustic paths between a source and the ears can be considered linear and time invariant. The measured transfer functions called the head-related transfer function can be used to simulate the effect of a single sound in free field. There are many different open source HRTF datasets. The earlier that I know of is the MIT ChemR dataset, which we have used quite a lot over the years and are quite thankful for it. And there's a CEPIC dataset, and there are many others that you can find online. It is also important to note that since anatomies of two different individuals are different, their HRTFs will be different too. And the mismatch between a listener's own HRTF and the employed HRTF dataset will result in decreased subjective localization, and in many cases, inside the head localization, which is something which is obviously not preferred. When synthesizing the acoustics of a room, we have more than one source, which can be individual sound sources, as well as room reflections or diffraction components, which we discussed before. These components can be processed using HRTF filters that correspond to their directions and edit. It is important for the XR system to respond to the head movements and update the necessary filters. And it is very important to update the system parameters fast, since any latency above 85 to 100 milliseconds will be noticed as a mismatch between visuals and sound, which will break the feeling of immersion, which is what we're after anyway. And the number of sources and reflections to be rendered will determine how many HRTF filters need to be used and updated. That means in that short period of time where you're handling head movements, you will have to deal with all the update of the system, including all of its filters, all of its HRTF filters, etc. An alternative approach popular in XR applications is transcoding higher order ambisonics content for playing back binaural audio. It is a clever, albeit not so new method. Transcoding multi-channel audio to binaural or playing back multi-channel audio in binaural rendering has been around for at least 2 decades now. Using this approach for ambisonics, higher order ambisonics makes it much easier, some of the things that needs to be done. So transcoding is achieved by keeping moving between these different formats, higher order ambisonics and binaural, is achieved by keeping a fixed number of HRTF filter pairs, 1 pair for each loudspeaker channel, which is involved in the playback of higher order ambisonics encoded sound. And assuming that we have an nth order higher order ambisonic signal, we will need n+1 squared HRTF pairs. The main advantage of this setup is head rotations can be handled in the spherical harmonic domain using the higher order ambisonics signals directly, and the need for updating the HRTF filters thus vanishes. However, this approach requires the synthesis of higher order ambisonic signals for the room that is going to be simulated, which would still require the simulation of direct sound, early reflections of the room, as well as ambisonics-based reverberation. So some important research problems related to binaural synthesis are filter design and interpolation and individualization. And there have been many papers written on these topics. HRTFs are typically represented by fairly long impulse responses, and having a large number of HRTFs in binaural synthesis scenario would typically be very undesirable in interactive systems. This led to research into designing simplified HRTF filters, much shorter, perhaps lower order filters, which can be used in such interactive systems. Another issue that needs to be solved is HRTF interpolation, which is especially relevant in XR for synthesizing moving sources. And there are several different methods to achieve HRTF interpolation. Some of these are directly carried out in the spherical harmonic domain, which means it provides some compatibility, some increased compatibility with higher order ambisonics transcoding as used in binaural synthesis. And an exciting recent addition to the several methods to solve this problem that uses computer vision was developed by the Finnish loudspeaker manufacturer company Genelec for binaural monitoring of audio bits. I would think that that would be quite commonplace in a couple of years for individualizing HRTFs for XR applications as well. So how can we integrate then binaural synthesis with room moralization? The figure in this slide shows the generic approach taken by many binaural oralization systems. The model combines all the necessary building blocks for oralizing an anechoic sound signal in a room. You see that the upper part is related to modeling and the lower part is related to oralization. Reverberation is typically a separate process which has to be retrofitted to the simulation. So with modeling, what you do is you calculate valid and visible image sources and diffraction terms, and then you use an anechoic signal and process that anechoic signal with HRTF filters, material filters, air absorption filters, and carry out interpolation on HRTF filters to synthesize direct paths, early reflections, and edge diffraction components. Then again, you add artificial reverberation. And as with any interactive audio system, you need to care about the head position and direction. So more specifically, what we might call as the direct oralization approach comprises an interpolated delay line for obtaining delayed copies of the input anechoic signal that would correspond to early reflections to be simulated. Now imagine, so this is a model for a single source, you would need multiple of these models for simulating multiple sources. So each of the delayed copies obtained from the interpolated delay line are processed in several stages to add propagation loss, air absorption, wall absorption, and direction. Direction is added by using HRTF filters. And artificial reverberation is typically independently chosen and uses decorrelation to generate binaural audio. Now, this is a very well-structured model, which has been in use for the past 20 years at least, but it has some important problems. So first of all, a good auditory user experience is possible if a high number of early reflections is calculated and updated at runtime. Combined with the validity and visibility tests, this will increase the computational cost greatly. A large delay line is needed to hold as many samples as the latest arriving early reflection requires. This will increase the memory footprint and will be especially not ideal for resource-constrained devices like mobile devices that we use in some cases. Using a high number of reflections means using correspondingly high number of filters that need to be updated and interpolated at interactive rates. And multipath reflections require a cascade of wall absorption filters, and these filters also cannot share memory, which means you would need many wall absorption filters in this case. Finally, the quality of artificial reverberation will determine the overall experience, and design choices will heavily influence the end result. So overall, the direct oralization is not a scalable approach. By the way, direct oralization is not a term used frequently, but it's a term that we have coined because this includes everything in different stages. So it is not a common term. So several different solutions have been proposed for solving some of these problems. And now I'll outline some of these specific solutions. So the first problem is with keeping the computational cost balanced, keeping it fixed. So it is well known that the transient parts of signals, sound signals, are perceptually more important than stationary parts of signals for directional localization. If you search for the transient effect, you're going to see some really interesting research into how the onsets are localized in stereophonic reproduction when you present the onsets of sinusoidal signals from one loudspeaker and the sustained part from another loudspeaker. So it can also be assumed that the direct path component and early reflections are not present at the same time at onsets. So when there is an onset, you're going to have the direct path component first and then the early reflection components. So this understanding led to a dynamic fixed cost model which uses a single cascade FIR filter structure per ear to oralize the direct path and the early reflections. The model has tunable blocks that will process either a portion of the direct path head-related impulse response or the first part of an early reflection head-related impulse response. So that is the block in red rectangle that I'm talking about. So you're using the same block for different purposes, and it's dynamically reset based on the state of the simulation. So when there is an onset, this will trigger the structure to oralize only the direct path component until the first early reflection arrives. The model then gradually starts to oralize early reflections. So each of these blocks within the model are executed when a certain duration has passed from the onset. So while this model requires the calculation of onsets, this can be made offline in many cases, and onsets can be stored alongside anechoic signals to be oralized, which makes this a very good alternative to direct oralization. Another approach to reducing the computational cost is culling reflections that will be suppressed and be rendered largely inaudible due to the precedence effect, or simply due to their levels, for instance. Image sources that represent reflections can be clustered in time, and the direction, depending on directions, they can be clustered further. And suppressors are identified for each cluster, which will be representative early reflections, representative image sources for that given cluster. And this way, it is possible to reduce the number of early reflections substantially without substantially affecting the auditory experience negatively. And finally, how you carry out binaural oralization in SDN. SDN provides a very simple approach that addresses all the problems with direct oralization. First and foremost, SDN bundles reflections naturally. That is, you have a single node that cares about the reflections from left, right, front, back, top, and bottom. So binaural oralization with SDN is possible by positioning a virtual head inside an SDN model. And each node-to-head connection requires a pair of HRTF filters. Head tracking can be almost trivially integrated into SDN. And source directivity can be simulated also in a very straightforward way. Finally, only a fixed number of filters would be necessary per reflecting surface in the model, which would reduce the computational cost even further. So here is a short demo about how SDN handles interactive oralization. I think Enzo would be in a better position to start the video.
You just need to move on to the next slide.
Oh, okay, that's good.
Yeah, that's it.
He stole a kiss in the changing of the reels.
Yep, Hseyin.
Yeah, I'm not entirely sure if it was heard the way it was intended to be heard, because I wasn't hearing it the way that it should have been heard. But it's good to see some smiling emojis, which probably means that people have heard it in the way that it was intended for.
It sounded great.
So, okay, excellent, great to hear. So now I'm going to leave the presentation on to Zoran, who's going to talk about examples of open source VR and AR audio rendering software. Here, Zoran?
We can't hear you so far.
Yes.
Maybe you have to unmute it.
Yes.
Yeah.
Can you hear me now? Yeah. Okay.
We can, yes.
By the way, I couldn't hear anything of the demo, but doesn't matter. I've heard it. So yes. So I'm going to give a quick overview of open source SDK for XR.
I'm sorry, Zoran, to interrupt, but I believe you need to amplify your voice. Again, host tools, and then...
I believe I did that.
Yeah, I mean, I'm back in the audience. And
Can you,
that's much better.
Can
That's
you hear
better,
me
yes.
better now?
Yes, yeah,
Okay.
yeah.
Okay, let me move. So yeah, where am I? So open source SDKs basically explore different trade-offs between the quality of synthesized room acoustics and associated computational complexity. Facebook's Audio 360 is a particularly lightweight. It allows for source directivity and different options for source distance attenuation. Modeled environments are cuboid rooms, and only early reflections are rendered given room dimensions, frequency-independent wall absorption, and maximum reflection order. There is a possibility for additional control of the overall level of early reflections, frequency absorption of the room to simulate empty or full rooms, and focus effects which attenuate early reflections outside of a desired region. And whilst late reverberation is not modeled, there is an option for integration with users' preferred late reverb plugins. Oralization is done binaurally in combination with up to third-order ambisonics transcoding. Google Resonance, although optimized for mobile devices, it includes some additional features. Most importantly, these additional features include occlusions and diffractions that are modeled as slowly varying low-pass filters, which emulates the effect that low frequencies are less affected by bending around edges, and there is also a built-in reverb engine that renders late reflections. So I'm going to talk now in a little more detail about room acoustics modeling. So this environmental acoustics is rendered within audio room's environment that exists there in resonance audio. And resonance audio, as a difference to Facebook's Audio 360, offers a large bank of surface material filters to model frequency-dependent absorption. And similarly to Audio 360, there is a parameter which can control the balance between high and low frequency content to simulate empty or full rooms. Again, only early reflections are rendered accurately, and the reverb engine renders some general late reverb that changes in real time, actually, with room dimensions and surface materials. In addition to point sources, which are spatialized in real time and for which monophonic dry sounds are used, there is also an option to use the so-called ambisonic sound fields to render distant ambisonic sounds, and that saves some of the computational load. Valve's Steam Audio provides some additional powerful capabilities. One interesting feature is that it allows for custom HRTFs, and it allows for gradations between modeling options such as partial occlusions, also occlusions by partly acoustic transparent objects. It allows for customized acoustic materials and offers different capabilities for handling dynamic geometries. Most importantly, Steam supports high quality reverberation, which is done by powerful ray tracing to generate impulse responses, and that is then followed by convolution. And since that is computationally demanding, it supports multi-core CPU and GPU acceleration. Little more detail of the high quality reverberation. It has several custom presets, the length of impulse responses, the maximum order of reflections, the number of rays in calculating impulse responses in ray tracing, then also the number of rays in calculating diffuse reflections. I forgot to mention that Steam also allows for modeling of diffuse reflections, the maximal number of sources which are rendered with high quality reverb, and also the amount of CPU time allocated to environment simulation. Some would actually see this as basically that there are limits up to which we can actually provide this high quality reverberation. So as we increase either one of those parameters, we obtain high quality, but that actually leads to much higher computational complexity. And as this high quality room acoustics is done via ray tracing and convolution, it requires powerful ray tracing algorithms. And in addition to its internal ray tracer, Steam supports also to external algorithms which are GPU or CPU optimized. In addition to that, it supports a specialized SDK for accelerated GPU and multi-core audio. The bottom line is that high quality environment acoustics via ray tracing and convolution comes at a price of high computational cost, as well as a considerable skill not only in multi-core CPU and GPU programming, but also in balancing the trade-off between the quality and complexity. And we are going towards the conclusions now.
Hseyin?
Yeah, sorry. In conclusion, physical room acoustics rendering provides high accuracy, but computationally, it is computationally very intensive, even in coarse approximations. So within an XR context, it is not probably the preferred choice, at least not right now. And leveraging perceptual phenomena enables to reduce complexity. That means if you don't want, well, if your user is not going to hear it or if whatever you produce is not going to have a big impression on your user perceptually, then you don't need to process it. So that is the main point that results in perceptual simplification methods. And hybrid methods, we think, are most suitable for XR. Hybrid methods that process early reflections and artificial reverb simultaneously. And recent developments in interactive room organization, such as SDNs, source culling, and other methods promise increased auditory user experience in XR without increasing computational complexity. So the research area is vibrant, and we expect to see more elaborate room acoustics and oralization models. One area which is particularly interesting is modeling of acoustics of maze-like structures, modeling and oralizing acoustics of maze-like structures. It is not only for immersive systems like this one, but for 3D games as well, especially for first-person shooters. You would need to emulate acoustics of maze-like structures. Then room geometry estimation is another topic which is relevant. Computationally effective simulation of edge diffraction is a topic which is of interest, because when you have occlusion, that is your first access to the sound that you're listening to in terms of its direction. Sound source and diffraction culling are two topics which are important. Again, that links to perceptual simplification of room acoustics models. We have GPUs, why not use it? In many cases, it's the executive decision from the company who is developing the XR system, but it is a topic of interest for making room acoustics emulation faster. And there are emerging applications of deep learning in room acoustics, which are probably going to feed into immersive environments directly in the near future. One additional, or I would say two additional things that I would need to mention here are two standards. Some of you might be aware of these standards, some of you might not be aware of these standards. But the first one is object-based audio, which was standardized in 2015, if I'm not mistaken. And the standard is called MPEG-H 3D audio, that allows you to deliver audio objects instead of channels, audio channels. Well, it also allows delivering channels, but the main idea behind MPEG-H 3D audio is object-based audio, which allows you to deliver sounds as objects. That is, you're giving the user of your XR application the possibility to modify whatever content they receive from the network. This is fully compatible with 3 degrees of freedom applications, and it allows parameterized representation of audio objects and reverberation. And it also provides transcoding tools for channel-based, such as binaural audio, and scene-based, such as ambisonics and OBA representations. That is not very popular right now because not many people know about it, but I think they should. So that is one thing that I would like to talk about. And another is the MPEG-I standard, which is still in the works. This is again about delivery of immersive experiences. It is, well, audio component at least is based partly on MPEG-H 3D audio, that is object-based. And MPEG-I will provide, when it occurs, all three different modes of immersion. That is 3DOF, 3DOF plus, which allows you to move your head just a little around your current listening area, and 6DOF, which allows you to move about the environment just as you would do in Altspace VR. So the work is in somewhat slow progress, but it is progressing nevertheless. And the main idea, I would say the holy grail, which resulted in MPEG-I, is for creating content which allows you to traverse, to move inside. So from the audio side of things, we're looking at audio content generation that will accompany fully immersive 60 RF video, that is actual recordings of people, actual recordings of environments or documentaries, which you will have the chance to move about with it. So these are two things which we will see more of in the near future, I think. And I think this is going to conclude our tutorial. We would like to thank you all for joining us. And we would be very happy to answer any questions you have or take your comments.
Okay, can everyone hear me?
Yep.
Yes?
Okay. So everyone should be able to see a little hand emoji in the lower right corner of their screen, and feel free to click on that if you would like to ask a question.
Sure. I have a question for you guys. In the last video demo you played, it looked the plugin, and forgive me if you went over this and I just missed it, but as you were spatializing some of the elements of the track, which I wasn't immediately able to tell, but I could tell they were moving, like whether it was the guitar or perhaps another aspect of it. Could you just elaborate a little bit on that particular tool and what you were doing with it, if that isn't too much off topic?
I believe it's not off topic at all. Who would like to answer, Hseyin? Should I answer?
Well, and so why don't
yeah.
you answer? Yeah.
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 So we had two separate demos. In one case, we had a demo that was assuming a stereophonic reproduction system. And in the other case, we were using a binaural reproduction exactly as Hseyin has described. So that was the second demo. So would you like me to go a little more detail in one or the other?
Yeah, the second one, if you can, without, yeah, that would be great if you could.
Yeah. So in that second demo, we had a number of sound sources that were all rendered within that room that you could see from above with the different dots. And for each sound source, we were simulating a virtual head and using specifically the HRTF dataset from the KEMAR database. And yeah, we were, as sound source was moving around and all the delay lines were updating so as to keep the scattering nodes in the close to position of first order reflection, together with updating the HRTF filters as well. And in that case, we were just using simple linear interpolation of the filter coefficients. And yeah, would you like me to go into? Does that answer your question, Lawrence?
That does. That was
Yeah.
great. Thank you very much.
Yeah. I believe there was somebody else with the hand raised, but I'm not entirely sure if I'm the one that's supposed to. Should I say?
I'll call on the hands.
Okay.
I did notice, Jeff, if you still want to ask your question, you might have to hit the button again. I'm not sure if you meant to lower your hand.
I did mean to lower it because he answered my question. Actually, it was just in regards to.
If not, if anyone else would like to raise their hand, feel free.
Megan, Jeff, I don't know, you might not hear that Jeff was talking and he was, maybe you can't hear Jeff. But anyway, go ahead, Jeff, finish your comment.
Just that the difference between using SDN and in early reflections versus reverb, but I believe you just answered that for me.
So,
in other words, SDN is applicable to both early reflections and late reflections.
Yes, I mean, and what it does is that it renders early reflections correctly, and then higher order reflections with progressively coarser resolution as they become less perceptually salient. So there is a little bit of error on second order reflections, a little more error on third order reflections, etc.
I see. Okay, thank you.
But we managed to render all relevant perceptual aspects without any kind of specific tuning. like direct reverberant ratio, echo build-up density, T60. We've done some, in the paper which we published, we can see that we are actually, SDN is performing exactly as image source method according to all those parameters.
Excellent. Thank you.
Thank you.
Do you have any other questions? Megan, go ahead.
Hi. It might be just because I don't understand the same level of like object-oriented for the MPEG-I, but you talk about like walking around in it, and also as a file format. I guess, is there like a limitation based on the actual engine that's being rendered? Because I would assume that if you're in SIGSTOF, you're relying on the engine to do the calculation portion of it. But again, this might just be because I don't understand the fundamentals.
Yeah, there are different ways that you can handle 6UF audio. One is using multiple recordings of high order ambisonics signals. Say, for instance, there's a Polish company called Zilia that you may be aware of. They have this 6UF recording mode by deploying multiple of their Zilia ZM1 microphones. That is one option, and the other option is using basically extracting audio objects or designing audio objects into your experience and positioning them within the virtual environment, which would then allow you to experience the directions as well as the environment, which includes those sound sources, by also allowing you to move about them.
Okay.
So as far as object-based audio, it is in a way very similar to how things are handled in game engines. That is, you have objects which also have attached sound effects, but it has been just a couple of years back, there's been the first radio broadcast with MPEG-H in Europe, and in that BBC, Fraunhofer, and others presented the content which can be modified by the content consumer while they're listening to the content. So that is also another application of MPEG-H 3D audio or object-based audio for that matter. But from an XR perspective, I believe it's going to be extremely useful as a complete tool set to not only deliver, but also to not only deliver content, but also it will allow the content creators to create content in a much more straightforward way. But I don't know if this answers your question.
No, I'm pretty sure it does. You don't need a game engine to do this, is I think my fundamental question. So, like, yeah.
Yeah, okay. Well, I mean, in the first incarnations, I would say, of MPEG-H 3D audio, you don't, well, the institutes that developed those software tools did not use any game engine for that matter. They were just presenting simple user interfaces for the content consumer to play with sound. But you know, it's very flexible in that sense, so you can use it in game engines as well.
Oh, thank you.
All right.
All right, would anyone else like to raise their hand to ask a question?
I believe
Laurie,
Laurie has
go
a
ahead.
question.
Laurie's, yeah.
Hello. Thanks a lot for great summary and presentation. I would like to ask you to speculate a bit on the future of the technique. So what will be the final winner? Will it be a hybrid or SDN or fast ray tracing or even some FDTD real time? What is your guess?
Hseyin?
I believe it's going to depend on the application, Larry. I mean, well, if you're trying to simulate the acoustics of a room that you're going to design like a concert hall, then obviously simplified approaches like SDN won't cut it. However, still for architectural walkthroughs where interactivity is key, you could still use hybrid techniques like SDN for that purpose. It is hard to tell. I mean, personally, I would be very happy, for instance, to see physical models, to be at a point where we are using them in real-time applications, interactive applications, and I'm hopeful about that. But most likely, again, that's just a speculation. It's very likely that simpler models will be key to delivering content in applications like this one, like Altspace VR.
Yeah, makes sense. Thanks.
It was, yeah. Sorry, I'm wondering if you're able to hear what I was saying.
Yeah,
My voice was not amplified.
People could. It was just not very loud, but
yeah. Okay. Sorry about that.
Do we have any other questions?
Well, I would just like to take the occasion to thank the organizer, Lawrence, Megan, everybody. It was a courageous choice, I believe, to choose this platform, and but I believe if somebody had to do it, it would be AVAR AES, so that made sense. I just wanted to thank you, and it seemed to work fine, at least for us, so.
It was fun.
Yeah.
Yes,
yeah,
thank
definitely.
you. Thank you, everyone. This is Sally again. Thanks for your wonderful presentation, all the examples, and for answering so many questions as well. Our next session in this room is at 2 o'clock, and that is with Brian Schmidt on Beyond Physics, the Limitations of Human Hearing and How Source Content and Human Expectations Affect Sound Localization. So everyone go grab some lunch, some dinner, some breakfast, some coffee, whatever it is that you need right now, and we'll see you back here at 2 o'clock. Yay,
Great
thank
job,
you.
guys.
Thanks.
Thank you very much for.
Thanks, yeah.
Yeah. Thank you.
Thank you very much for attending.
Some great style from avatars. I see blue people. I see Edgar here in the front. I believe has some back problems that maybe he's going to at the first row.
He needs some
people
chiropractic.
Some people left their hands 3 meters away.
Yeah.
And then I saw Superman in the middle. That was fun.
I should mention that if anybody still has energy, you can you might. I haven't been there, but you might go over to AVAR Lobby, which is sort of the in-between space. You can hang out at DigiPen there and chat with your colleagues and friends. If anybody has the stamina for it, feel free to do so. Otherwise, I hope you'll all join us back. Sally, you said it was at 2 o'clock for our next workshop. Is that correct? I think that's what she said. So.
Yes, 2 o'clock.
Yeah, great. All right. Well, thanks everybody.
All right. Thanks, everyone.
Thank you very much. Thank you.
Thank you.
I'll go to the lobby now.